let's see. Last time I was basically saying that we had finished talking about undecidability, but that undecidability is a very formal way of talking about what computers can't do, or provably can't do. And that really the moral of that kind of study is broader than just the question of deciding or recognizing languages. And as one reflection of that, I just wanted to talk a little bit about functions and whether computers can compute all functions. And you'll see that really we have all the tools to address that kind of a question too, even though it sounds on its face somewhat different than the question of deciding or recognizing languages. So remember, a function, we go from a value here, x, let's say this is a function of integers, to another function, so let's say to another value, x squared over 3 plus 42 minus x. That's a perfectly good function of x, and given a value of x, you apply this and you get f of x, all right? So is this a computable function? I mean, what do I mean by a computable function? Is there a Turing machine? Is there a Turing machine which can take in x and then, after its computation is finished, leave on its tape f of x? Okay, what the value of f of x is. Okay, so inside here it's doing its computation. And what do you think about this one? Yeah, it seems pretty simple. I mean, you can think about how a Turing machine would compute x squared. Let's say x is taken in as even as unary. The number of ones here is equal to x. And how would we compute x squared? You would, actually, we have this division by 3. Let's get rid of that for a minute. Okay, so we can talk about this more easily. But you take an integer here, and how does a Turing machine square it? Well, for every one it sees here, it wants to make this copy here that many times, make an additional copy of that on its tape. So if we had, just to make it a little bit simpler, if we had 3 as input, we want to make one copy of it for that one, and then one copy for that one, and then one copy for that one. Okay, 9. So Turing machine, you certainly can write a Turing machine or develop a Turing machine that can take in x and leave x squared on its tape, and then plus 42. Well, that's a constant number, so that can be built into the Turing machine mechanism. It's a constant fixed number, so it would write an additional 42 of these markers. Okay, and then x. Well, again, it has x. Imagine if it has another tape. So we know we can use multi-tapes. Another tape where it's recorded what x is off to the side, and then it just has to go and, and for every one it sees here, it removes a 1 there, removes another 1 there. So definitely this function can be computed by a Turing machine. All right. So the notion of a Turing machine computing a function and leaving f of x, the result of f of x on its tape, should be fairly natural. Even though we're no longer into accept and reject, we're into this sort of a model. Although I mentioned last time, you could also think of this, think of a Turing machine as taking an x and then y, and then testing if y equals f of x. Okay, that's another way of thinking about whether a Turing machine can compute this function, because then this is in the context of accept or reject. Okay. All right, and then we left with the question: is there a Turing machine? I want to get the grammar of this right. The quantification. Is it true that for any function f, there is a Turing machine M of f that can compute f. And again, by compute f, I mean it takes in an argument for that function and it leaves f of x on its tape. Okay? So do you think that this is true? Is it true that for any function f, there's a Turing machine that can compute f? And then we have a yes or a possible no. Multiple choice. What's the right answer?
Yes.
Who said yes? Yeah, and what's your reasoning?
Don't we already have computers that compute functions?
Yeah, say it again louder.
Don't we have like computers that can graph functions and everything?
Oh, okay. Your proof is that you have these handheld graphing calculators, Texas Instrument, and you can plug in any function that you can think of, and it does graph it. So therefore, it must be computable. That's not a bad argument. It's wrong, but it's not bad. Any other? Yeah.
I have a question about what constitutes a function.
Well, a function is a function. It's what you learned in grade school or high school or wherever. It's just that there's a single value, f of x, for each x. Okay? It doesn't mean that that value is different. It could be for 1, 2, these get the same values. Here's f of x. But the point is that it maps each element in the, I guess this is called the domain. I've forgotten how those things are called. In the domain here to exactly one value in the range. Okay, that's all. And these values could be different from each other, or they could be the same, like these two are. Okay, and the range could be natural numbers, or it could be. You can make up different ranges, but yeah. Does that help you answer the question?
Yeah.
And what's the answer you have?
Yes, by intuition.
Yes, by intuition. Okay. All right, so I guess we have 2 yeses. Anybody else? So it must feel to you that computing a function is somehow easier than recognizing or accepting languages, because we've seen that there are languages that no Turing machine can recognize. Mostly we've been talking about Turing machines deciding. We also had one language that a Turing machine couldn't recognize, and we had many languages that Turing machines can't decide. Okay, so that we know there are definitely undecidable languages. Yeah.
When you say compute, do you mean find the exact answer or find an approximation to the nearest whatever?
No, you have to find the exact answer. Okay, so these are, even if we restrict functions that are integers to integers, okay, so then there's no issue of approximation or round off or any of that kind of stuff. So we'll just even specialize it to simpler functions like integers to integers, okay? Then, okay, well, how about this function? Is this a function or not? Okay, the input is a description of a Turing machine. Okay, you can even make this in binary if you like, because we know binary alphabet is able to describe. But at any rate, this is a description of a Turing machine, and f of that input is equal to 1 if m always halts. and 0 if m sometimes does not halt. Okay. Well, we're taking here we're taking strings, which you can think of them as numbers. Okay, the description of this Turing machine you can think of as a number, or and then here the value f of m of this function is going to be 1 or 0. Okay, and it's going to be 1 in the case that m always halts, and on any input, and 0 if it doesn't. I mean, that's a perfectly good function from well, it's actually what's called a partial function, because there are values here which are not true descriptors of Turing machines. So we can add in, if it's not a descriptor of a Turing machine, then its value is going to be 0. If it's a Turing machine that always halts, then it's going to be a 1. Okay. And does this solve the halting problem? So if you feed in what is a true description of a Turing machine, and you see whether this f, if this was computable, you could just see whether the value is 1 or 0, and that would tell you whether m halts on all input, which we know is an undecidable problem, undecidable language. The language of all Turing machines is undecidable. So all I'm really doing here is just saying that even when we have this context of functions, then we can apply what we know about undecidable languages to say that there are these uncomputable functions. Okay, so again, I didn't write up exactly what it means to be computable. Computable means that there's a Turing machine which can take in an element of the domain and leave on its tape f of that input value x. Okay, all right. So this is sort of the quick way of seeing that. Well, with everything we know, there are certainly uncomputable functions. But let's suppose we didn't know all this. Let me just give you a quick direct proof, or another proof, that there are uncomputable functions. There are uncomputable or non-computable functions. And this is just going to be by diagonalization. Okay, so every function, to be computable, remember, to be computable means that there has to be a Turing machine which computes that function, which can take in an x and leave on its tape f of x. We know that Turing machines are enumerable. Okay, we can put the Turing machines in one-to-one correspondence with the integers. So we can put the computable functions. Well, yeah. Here's f1. That's the first function. The second function. Okay. The nth function, and so on. So we can have a listing of these functions, or equivalently, we have a listing of the Turing machines that compute the functions. Okay. M, n, and so on. And then here, let's say these are just functions over the integers. Okay. Here we'll have a listing of the integers, and then what do we have, let's say, for the ith Turing machine, we'll just, in that ith row, or the ith function, in this conceptual table, we're going to have f of 1 here, fi of 1. What does this function compute when it's given 1? Okay, so fi of 1, here will be fi of 2, and so on. Fi of 6, all right? Okay, now I want to argue. So this is the list of all the computable functions. and this is how they behave on all the input. And I now want to argue that there's a function, perfectly legitimate function, which is not in this table. Okay? Who can tell me how to create one? The hint begins with a D, ends with an N. Yeah, diagonalization. So we're going to create a function which on input 1 is something other than f1 of 1. Whatever this was, whatever f1 of 1 was, the new function I'm creating is going to be something different. Okay? And then on input 2, it's going to be something different than f2 of 2. And so on all the way down the diagonal. So we have fi of I. It's going to be different than that. And down the diagonal, fn of n. Okay? Well, that's a perfectly good function. It says what is. Let's make up a name for that function. Function g. It's a diagonalized, or d. Function d. So what d of 1 is whatever I change this thing to, this entry to. D of 2 is whatever I change this entry to. D of 3 is whatever I change that entry to. Okay? Perfectly good function. For every integer, function over the integers, for every integer value, there is a definite value d of that. So for every I maps to d of I is well defined, completely defined. So d is definitely a function. Okay? Well, d is a function. This is the list of all computable functions. Where is d in this list? It's nowhere in that list, because wherever you say it is, if you say, oh, I think it's here at position k, so we have fk, I conjecture that d is equal to f of k. Okay, f sub k. But that's not true, because if you go out to the diagonal, here we have fk of k, and what d is equal to, d of k is not equal to fk of k. That's how I constructed the function d, by diagonalizing, by getting values along the diagonal that were different than what's in the table. And so d cannot be any particular one of these values f that is in my listing of all the computable functions. So there are uncomputable functions. So this is a way of, the diagonalization is just a simple, straightforward way of arguing that there are uncomputable functions, whereas over here we're actually able to exhibit one. Through all the things that we did about undecidability, we have more than just that they're undecidable languages. We actually know some specific languages that we can point to and say those are undecidable. Okay, and similarly we can create uncomputable functions like this one, but it feels a little contrived. Whereas this feels a little bit more natural of what a function is, and then this argument shows that they're uncomputable functions. Okay, this is a pretty simple argument. I hope everybody got this now after we've been talking about so much about uncomputability. This should be pretty understandable. So understandable that I used to say that when I taught, the last time I taught this class was 12 years ago, but I said that I could do this proof while standing on one leg. Okay, now I don't think I can do that anymore because my balance isn't as good and I need two boards and I have to hop around. But really think that every one of you ought to be able to do that proof while standing on one leg. And so you can teach that statement to your friends. But this, as simple as this is, this was a very profound and disturbing fact when it was first enunciated, like in the 1930s or 40s. Of course, the whole notion of what was computable wasn't articulated until about that time as well by Turing and others. But prior to that, it was just sort of assumed that, well, any function somebody could think up, you could have an algorithm, you could have a machine ultimately that could compute it. That was just their intuition about machines, and what this whole theory that we're looking into is telling us right now is that that's not true. There are things that are just not, there are languages that are not recognizable or decidable. There are functions that are not computable. Okay, and I mentioned earlier, when you translate all this over to logic, Gödel showed in a very similar kind of way that there are statements in arithmetic, statements about arithmetic, that are true but are not provable. Okay, so the context of that kind of proof is more complicated than what we've been doing, but the ultimate logic of this kind of diagonalization or self-reference is the same. And the Sipser book has a little bit of an introduction to that, to Gödel's proof, and a sketch of it, so you can read that if you want. So all this, before we move into the next topic, this just reminds me of the story I wanted to tell you, which is there are many books about Turing. He was a very interesting character in addition to being very significant. But there's also a play about Turing. I've forgotten what it's called, but I saw it. Has anybody seen a play about Turing? Or they made it into a movie also. At any rate, he in World War II he was one of the principal people in code breaking of the German U-boat code, and which happened at the place called Bletchley Park. So they had a lot of weird characters working there, and he was one of the weirdest. And so in the play, he's being interviewed by the manager of Bletchley Park, who's a military type, is not really into all this stuff. And Turing is kind of so this is during the interview, and Turing is going on and on about uncomputability and undecidability and all this. And you see in the play or in the movie the manager getting more and more fatigued as Turing is just going on and more animated, and it seems like hours go by, and the manager is getting more and more distant. And finally, the manager wakes up and says, "Okay, wait a minute. Let me get this straight. You have invented a machine that cannot be built to prove that there are problems that cannot be solved." And Turing said, "Yes, you've got it. That's it. That's exactly what it is." So that's what we're learning about. We're learning about Turing machines, which, think of it, if it's got an infinite tape, it really can't, it's an idealized machine. It can't really be built. To prove that there are problems, functions that cannot be computed even on such a mythical machine, and there are languages that cannot be recognized on it as well. And so, okay, so that's the story. But that reminds me of the particular point that Turing machines, if the Turing machines can't be built, why do we care about them? Well, if every real machine, the Church's thesis is that every real machine, every real computing device, whatever its behavior is, can be simulated by a Turing machine. So even if Turing machines have this extra power of having an infinite tape, which real machines don't, if you show that there's something that a Turing machine can't do, then you've definitely shown that there's something that the real machines can't do. Okay? So it's okay to have your model be more powerful than reality if what you're going to prove is a negative result. Okay? If you prove, oh yes, something is doable on a Turing machine, well, usually the way we prove it is very much demonstrates that it can be done on a real machine, because we don't use the infinite, really don't use the power of the infinite tape. But if suppose you did, then it wouldn't necessarily be doable on a real machine, unless you said real machines can always get more memory when they need it. They just go to Fry's and buy another disk, whatever. They ran out of space. Okay, so this is diagonalization, uncomputable functions. If I asked you on an exam, a closed book exam, to prove that they're uncomputable functions, you should be able to do this. This is what I'm really think at this point. You should be able to do this. And 20 years from now, when you're in the middle of hacking some next video game or something, for what you really work on, you might occasionally remember, oh yeah, we learned this weird thing when I was an undergraduate, and there are functions that are not computable, and that should be something that's interesting, and that you would remember even how to do it 20 years from now. Okay, so now we're moving into the next chapter. Actually, I think we're skipping a chapter, and we're moving into, yes, I think the next chapter is something called Advanced Topics in Computability, which we're going to skip entirely. And the chapter after that, I think it's the book it says part 3 or something. So we're moving into complexity theory. Okay, so far, what we've been dealing with is questions of whether or not a Turing machine or a finite state machine can do a particular task. Can a Turing machine decide a particular language or recognize a particular language? And we didn't really concern ourselves with how much time, except for the distinction between finite time and infinite time. Does the Turing machine halt eventually? That's finite. Or does the Turing machine never halt? That's infinite. So that was really the only distinction when you thought about time. And now we're going to be more refined. We're going to really introduce a time or a clock into the model. Because the kind of thing we want to be concerned about now is, okay, we have some function that's computable. We have some language that's decidable or recognizable. But is it decidable efficiently? Is there some Turing machine that can decide that language quickly? Or are all the Turing machines that decide that language, do they all require a vast amount of time, even though it's finite, so much so that it's not really practical? Okay? So I'll be making all of those concepts precise, and then getting into what we know about that. Well, some of what we know, anyway. It's an introduction into, all of this is essentially an introduction. Okay, so first of all, again, f is, well, in this case, f is going to be a function from the natural numbers to the natural numbers. These are the non-negative integers. Okay? So f is a function. And the main thing we're interested in is the following. Given a, let's say, first of all, deterministic Turing machine M, okay, so this Turing machine is completely deterministic. When you give it a particular input, it does its thing, and being completely deterministic, it takes a certain number of steps, a certain number of transitions that that Turing machine takes. So given Turing machine M and input X, M takes, oh, I'm sorry. Why didn't anybody stop me? What I just said here, well, all right, maybe it's actually literally not wrong. M on input X takes a certain number of steps, except that one of those possibilities is that the number of steps is infinite, because maybe M doesn't halt on input X. Okay, so let's just first of all restrict this to deciders. Given a Turing machine M, which decides some language L, and an input X, M takes a specific finite number of steps. Okay. Because it is a decider, it always halts on input X, or input, whatever you want to call the input. M being a decider either accepts or rejects, and being completely deterministic, it takes a specific number of steps, okay, transition steps. And we'll just say that that's f of x, okay? That's defined as the number of steps on input x. Okay, so since for every particular input there is a specific number of steps, number of transition steps that M does, then this is a well-defined function. Okay. Actually, I want to change this F to something other than F. Let's say G. Okay, so G is also a function. All right. Then I want to define f m of n is equal to the maximum over g of x such that the size of x is equal to n. Okay? So x is input to M, and x has a particular size. It's given as a string on the input tape, so it has a particular size n. Okay? It's a string over the input alphabet sigma, and it has a particular length n. And well, this is, so the largest g of x, the maximum g of x, where the length of x is n, that's what f of m of n is going to be. Okay? So let me just put a little bit of a 1, 2, 3, 4, and so on, n. And so this is the, here I'm writing down lengths of x. Now for any particular length, we have different input of that length. And for one of those inputs, this is f of x. This is how much time, how many steps m takes on that particular input. And for some other input of that size, it takes this much, and for some other input of that size, it takes that much, and for some other input of that size, it takes that much, and so on. So for any particular length, n, there's multiple possible inputs of that length into Turing machine M, and each of them takes some specific number of transition steps in M, and so we can write it like that. And so if we did actually write out how much each of these possible inputs of length 4, how many steps M takes on that particular input, in this picture, where is f of 4? What is f of 4 in this picture? Sorry, this is G. But, okay, so this is how much time this particular input, this is associated with particular input x. This is how much this particular, how much time, how many transition steps the Turing machine takes on input x. And now I'm asking, where is, in this picture, f of m of 4? With the particular value of n being equal to 4. Yeah? Yeah, the top dot, okay? That's f of m of 4, okay? And so if I also had those dots for 3 and those dots for all the different values, then connecting the top ones, when you connect the top, that's fm of n. Okay, well, where n is the variable here. Okay? And this is called, this function is called, fm of n is called the worst case running time. We say running time, but it really is the number of steps. Okay? So worst case number of steps of Turing machine M as a function of input size or input length n. Okay? Now, I think in the book they don't use the subscript m, but I wanted to add this here to emphasize we're talking about a particular Turing machine. So for a particular Turing machine, this function is well defined. This is the worst case number of steps that m uses as a function of the input length n. All right. Now, I think everybody up to this point in your classes that you've taken has heard people talk about worst case behavior of some algorithm, or worst case behavior of some worst case complexity of some problem. Has everybody here, who's here heard of worst case in some context? Yeah, definitely you haven't. And if you've taken 122, which some of you have, some of you may not have, then you're focusing a lot on worst case behavior of specific algorithms. Okay, so this should hopefully be a fairly natural definition. All right, now we want to make a distinction between those functions that are bounded by a polynomial and those functions that are not. So what's a polynomial, by the way? That's something everybody's seen in high school. I'm sure you spent weeks or months talking about polynomials, but just like prose, something you've been speaking and writing all your life, you may not have a good definition of it. Okay? But what is a polynomial? Well, okay, so I'm not going to give you a full definition, but let's just say n cubed plus 3n. Is that a polynomial function of n? Yeah. And what about 3n? Is that a polynomial function of n? No, that's an exponential function of n. N is in the exponent. This was exponential. Of n, and this is a polynomial function. Okay? Polynomial functions grow slower than exponential functions. Eventually, as n gets big enough, if you show me a polynomial, no matter what it is, and an exponential, no matter what it is, as n gets big enough, as long as these are positively growing, as n gets big enough, the exponential gets bigger than that polynomial. No matter what polynomial you show me and what exponential you show me, eventually when n gets big enough, the exponential value, the function of that function, the exponential function, is bigger than the polynomial. So, in fact, let's say you were offered to be paid for n days of work, n squared dollars versus 2 to the n dollars. Which one would you prefer? Okay. 2 2 to the n generally, unless n is 2. Okay. If n is 2, and if n is 1, yeah, it's funny, if n is 1, then you get $1 here, and you get $2 there. If n is 2, then you get $4 in both cases, and then if n is 3, then this is 8, and this is 3 squared is 9. So it flips, but eventually, okay, this is what I was saying, this is a polynomial function, this is an exponential function. Eventually, 2 to the n comes to be bigger than n squared. So there is an n0 such that 2 to the n is bigger than n squared for all n greater than or equal to n0. There's some place where this flipping back and forth doesn't happen anymore, and 2 to the n dominates n squared. Okay, so generally, well, the answer to my question of which you would prefer, I guess, depends on what n is. But if I say, well, I'm not going to tell you what n is, but it's going to be big, then, of course, you would much prefer 2 to the n. This is a very rapidly growing function compared to n squared. And n squared is rapidly growing compared to n log n, which is rapidly growing compared to n. I mean, you should just have these kinds of feelings for the growth rates of different functions. Okay, so polynomial functions, we distinguish between polynomial functions and exponential functions, things that grow faster than polynomials. I guess there's always some debate about this function, n to the log n. Is that a polynomial or an exponential? It's sort of somewhere in between. I'm not sure what, but at any rate, it's all a matter of label. Polynomial, exponential are the main distinctions that we're going to be concerned with. All right, so we also want to talk about when one function eventually gets to be bigger than another function, and we have several different ways of talking about that kind of thing, and different notations. I'm just going to introduce one of those. This is really all we need. The book introduces two, but I think we only need one. Okay, so wrong chalk. A definition: f and g are functions. Integer natural numbers to, I don't know, here it's positive real numbers. F of n is big O of g of n if there are positive integers c and n0 such that f of n is less than or equal to c g of n for all n greater than or equal to n0. So basically this is just saying that, well, imagine if I took away the c for the moment. Then this would be saying that eventually this function f of n is less than or equal to this function g of n for all values of n greater than or equal to n0. We saw that over here. Okay, there's a value of n probably around 4, probably 4, such that 2 to the n is always greater than n squared for any n bigger than that 4. So n0, I think here n0 would be 4. And c could be 1. All right? But now here we allow a little bit of sloppiness because we have this extra c in here. So we give g this extra boost by multiplying by c. And that's for the purpose of being able to say things like n squared, let's say 5n squared, is big O of n squared. Okay. So if this plays the part of f, this plays the part of g, it never happens that f of n is less than or equal to g of n, because f of n has this extra 5, right? But we still want to say that 5n squared is big O of n squared, and we can because we can make c here in this definition equal to 5, or equal to 6 if we like, whatever. So the big O allows a certain amount of sloppiness, and you can kind of basically think of it as big O of some function is just the high order term of that function, where you ignore constants, you ignore the lower order terms, and that's what that is. So another example is 5n squared plus 32n is also big O of n squared. Okay? And how would we formally, in terms of applying this definition, how would we formally get that result? Because this always has this extra 5 and the n squared doesn't. And this always has this extra 32n and the n squared doesn't. So how do we ever get c times g of n bigger than 5 than this, f of n? Anybody see it? Do what?
Choose a c that is higher than 5.
Pick a big enough c. Yeah. And is that what you're going to say? And you have to convince yourself, well, it's just, again, a simple matter, that, well, for example, let's say I took 32, or actually, let's take 32 plus 5, which is 37. And let's make it 40 just for good measure. Okay? So if I take c equal to 40, c equal to 40, then I'm comparing 5n squared plus 32n to 40n squared. Okay? Well, which one of these is bigger? And this is even, I mean, according to the definition, we only have to show that this is bigger than that for all n bigger than some n0. But now I'm saying even when n is equal to 1, okay, because this has in it 32n squared, that's bigger than the 32n, and it has within it another 7n squared, which is bigger than 5n squared. So we get that for all values of n. So we certainly satisfied this definition. Okay, so that's what big O is. Basically, if you look at a function, particularly if it's a polynomial, or look at a function, and you identify what is the dominant term, what's the high order term, what's the term in that function that grows the fastest, and then you throw away all the constants that are associated with that high order term, and you throw away the low order term, then you can say that function that you've just given a haircut to is big O of what remains. Okay. How many people have seen big O before? I'm sure everybody, okay, all right. How many felt you know what it meant? Good. Okay, a couple of people. And in fact, there are other definitions, but this is fully correct. In 122, we give a more useful definition when it comes to trying to evaluate whether two functions, one function is a big O of the other. All right, so now we have all the little things that we need. Well, one of the things that the book does now is say that looks back at the Turing machine that decides the language A equals 0 to the n, 1 to the n, 0 to the n. 0 to the n, 1 to the n for n greater than or equal to 1. This is our old favorite non-regular language, and we saw early on when we started talking about Turing machines that a Turing machine can definitely decide this language. It just zips along. It looks to see that there's a 0 at this end. Well, first of all, it goes through and makes sure that there's never any 1s in front of any 0s. If there is, then it rejects. But if there isn't, then it goes back and forth between the 0s and the 1s, crossing off a 0, crossing off a 1, crossing off a 0, crossing off a 1, going back and forth like that until everything is crossed, or until all the 0s, let's say, are crossed off and it sees if there are any 1s left, or all the 1s are crossed off and it sees if any 0s are left. Okay, so Turing machine can do that. So if M is the Turing machine we studied, that I just outlined, to decide A, okay, what is Fm of n? Okay, the input size actually, because it has, I use this n to talk about how many 0s and this, and n to talk about how many 1s. If this down here is the input size, maybe I better make it 2n, because that's, in terms of n, that's the size of the input. Who stole my chalk? Yeah, I lost it. Can anybody see, sort of offhand, what f m of 2n is? Remember, this is the Turing machine that's shuttling back and forth, crossing off a 0, crossing off a 1, crossing off a 0. Yeah.
2 is basically how many characters on the tape, right?
It's what? 2n is, yeah, the number of characters on the tape, right.
So it has to be at least 2n steps, right? Just by making sure you have to go across it.
You're saying it has to be at least 2n.
Right.
But is it bigger than 2n? Anybody else? Yeah.
Do you count like every step, like going from the 0 all the way to the next one?
Every transition the Turing machine does. So when the Turing machine moves its head from one position on the tape to another position on the tape, that's a move. That you have to count that. Yeah.
Well, our close upper bound would be 2n squared, because for each of those 2n, you have to cross essentially all characters.
Yeah, and is that what you're going to say? Yeah. This is big O of n squared. The point is this n squared, because you're shuttling. You'd have to look back at exactly at the details, maybe, to convince yourself of details of how m works. But it's crossing off a 0 here and then going down n positions until it sees a 1, crosses off that, goes back until it sees that 0 that was crossed off. That's another n steps backwards, moves, crosses off the next 0. Then it moves how many positions? Another n positions to get to the next 1 that was not crossed off. So it's back and forth n positions each time it crosses off a 0 and a 1. And it does that n times. So it's n squared. Okay. Now there's maybe some little additional things in there so that you end up with n squared plus some constant. But then when we apply the big O, it all boils down to just an n squared. Okay, so this particular Turing machine has a worst case behavior that's at most it's bounded by big O of n squared. Okay, is that a question or yeah?
So I feel like that will only be for the Turing machine that zigzags.
Yeah.
The thing, right? Say if we had another tape that records like some kind of character when it hits a 0,
Yeah.
and it goes back when it starts hitting 1.
Right. Yeah, okay, so the first thing that's said is this analysis is for this particular Turing machine that we saw earlier in the course for deciding this language. You could possibly come up with another Turing machine where its behavior is different than this. Another Turing machine for this that recognizes this language, but its worst case behavior could be different than that. And in particular, what was also suggested here is if we allowed our Turing machine to have two tapes. Let's say we have a Turing machine that has two tapes. Turing machine M with two tapes. Okay, so in comes a string 0 to the n, 1 to the n, or some string, we don't know what it's going to be. The Turing machine, first of all, scans its input to see if there's a 1 in front of a 0, and if there is, then it already rejects. But if not, if all the zeros are before all the ones, then what it's going to do is make a copy of all the zeros on one tape and make a copy of all the ones on another tape, or even more efficiently, it could just scan through the zeros on the input tape, and then as it's scanning through the ones, erase them, but make a copy of it on some other tape. Okay? Now, how many steps does this Turing machine do so far, up to this point in this description? Just n. Okay? It's just scanning through here. Well, it's on the order of n. It's scanning through here to make sure. Actually, we can combine all this at once. It's scanning through here to make sure that it doesn't see any ones before a 0, and then and no zeros after a 1. But after it sees zeros, it makes sure it's just seeing ones, and it erases each one of them, but makes a copy over here. So the amount of work to do this so far is just big O of n. Okay? No n squared in there yet. And then what the Turing machine does is backs up its two heads to the beginning here. Or maybe, yeah, that's fine. Or actually even more, now that we're really talking about efficiencies, now we're thinking about all the different shortcuts. This might back up this head to the last 0, and this head is already sitting there at the last 1. Okay? So that was less backups. But at any rate, that certainly just takes order n work there. And then it just alternates erasing a 0, erasing a 1, moving over, erasing another 0, erasing another 1, moving both of the heads over, erasing a 0. And at the time that 1 hits the end of its tape, the beginning of its tape, it makes sure that the other one, it makes sure whether or not the other one has hit the beginning of its tape. Okay? So this Turing machine with two tapes and two heads can operate Fm of n is equal to big O of n. And so what I just outlined to you just takes order n transition steps. Okay? So this Turing machine takes n squared, and this one takes order n. Okay. Now, in fact, this doesn't prove, but illustrates a point that when you allow Turing machines to have more tapes, they can be more efficient. We already proved that in terms of what's decidable, what languages are decidable or what languages are recognizable, it doesn't matter whether a Turing machine has multiple tapes or not. Any Turing machine that decides a particular language using multiple tapes, for that Turing machine, there's also a Turing machine that decides that same language with just one tape. But the one-tape Turing machine is less efficient. It does a lot of extra moves in comparison. When you do that, when you look at that particular simulation that proved that point, there's a lot of extra moves that one-tape Turing machine does in comparison to the multi-tape Turing machine. So, and this is sort of a reflection of that. We haven't proven that a one-tape Turing machine, that there is no one-tape Turing machine that can decide this language in order n transitions. We just said this particular Turing machine uses order n squared, and we have seen a 2-tape Turing machine that can decide that language in order n transitions. But there isn't actually, I think it's true and known that there isn't a 1-tape Turing machine that can decide this language in order n transitions. So having more tapes does make the Turing machines more efficient, allows them to be more efficient in worst-case running time, even though everything that can be done on every language that can be decided or recognized on a multi-tape Turing machine can be decided or recognized on a 1-tape Turing machine. So multi-tape and 1-tape are equivalent in that sense of what languages are recognizable or decidable, but they are different in terms of how efficient the Turing machines can be. Still, there is a theorem which I'm not going to prove. I think it's actually proved in the book, that shows that things aren't too terrible. Now, let me just say it informally, because we only have 20 minutes left, and I haven't gotten as far as I wanted to. Just informally, and we're not going to prove this, but you can read it in the book, that if you have a multi-tape Turing machine, no matter how many tapes it has, and its running time is fm of n, then you can actually create a single tape Turing machine that decides the same language, or recognize it, depending if this is a decider or recognizer, which takes this amount of time squared at most. Okay, so you can do this simulation of multi-tape Turing machines by a 1-tape Turing machine and only square the total amount of steps that are needed. Okay, so that's in the book. And since the square keeps us within polynomial time, it means that anything that can be done, any language that can be decided on a multi-tape Turing machine whose worst-case number of steps is bounded by a polynomial function of the input size can be done on a 1-tape Turing machine whose worst-case number of steps is bounded by a polynomial in the input size. Because you take any polynomial and you square it, that's still a polynomial. Okay? The square of a polynomial is a polynomial. So with respect to polynomial time, it doesn't matter whether you're talking about a multi-tape Turing machine or a single-tape Turing machine. If you just want to say, yes, it's doable, yes, this language is recognizable on a Turing machine whose worst-case running time is bounded by a polynomial function, you can demonstrate that. If that's what you want to demonstrate for some particular language, you can demonstrate that by using multi-tapes if you want. Okay? Yeah?
Does that mean if you have a Turing machine, a single-tape Turing machine with a runtime of big O of n, that you can't get anything better by having multiple tapes?
You're saying if you have you have a single-tape Turing machine that has a running time of big O of n, can you do better by having multiple tapes? Well, generally, okay, you use the particular function big O of n, and let me just say more generally, if you talk about a particular function, can you do better on multi-tapes? And the answer is yes. I mean, there are plenty of examples where that's true. I wouldn't say it's always true. Now, if you're talking about big O of n, then you're saying, can something with multiple tapes do better than big O of n, which means that Turing machine wouldn't even look at all of its input. Just to look at each character on the input tape takes big O of n. So you'd have to think of a problem. You have to come up with a problem where it's possible to decide that language without even looking at all of the input. Okay, and there are languages like that. Okay, let's take the language. I mean, now I'm thinking of something completely contrived and trivial. The language of all binary strings, whose length is greater than 3. Okay? Now, does the Turing machine need to look, when it's given input, does it need to look at its all characters on the tape to decide that? No. It just has to see if there's 4 or if there are 4 or anyway, if there's less than 3 or greater than 3 symbols. Okay, but that's something that a single tape Turing machine could also do. So I don't know how to answer your question whether multiple tapes would let you do anything better than single tapes if on your single tape Turing machine your running time is already order n. I think that's quite unlikely that the multiple tapes would give you that kind of advantage. Okay. So we have that. So with respect to polynomial time, it doesn't matter whether you're talking about a multi-tape Turing machine or not. And so therefore, we don't have to be that precise about which Turing machine we're talking about when we talk about worst-case running times. Okay. Now, so we've been talking about the worst case, now I will call it running time, but whenever I say running time, I really mean number of transition steps. Worst case running time of a deterministic Turing machine M with respect, as a function of input length n. Now I want to talk about a similar thing for non-deterministic Turing machines. Okay, we want to talk about what's the worst case running time of a non-deterministic Turing machine as a function of its input length n. Does everybody remember non-deterministic Turing machines? We haven't talked a lot about them, but remember, every Turing machine is described by a transition function, which is here is a state, and here is what it's seeing on its tape, and then it goes to another state, and what it writes on the tape, and whether it moves left or right. Left or right. Right? And this is what a deterministic Turing machine does. It has, for every particular state and character pair, it has a particular state that it moves to, a particular character it writes, and whether it moves left or right. But in a non-deterministic Turing machine, you can have a set of possible transitions. And so this is a function, delta is a function from state cross character to a subset of the power set, some subset of all possible transition rules. Choices for what's the state you move into, what's the character you write, and whether you move left or right. So this is a non-deterministic. This is the kind of a transition rule you have in a non-deterministic Turing machine. And then we proved that, and then let me go back up a minute. What did it mean for a non-deterministic Turing machine to decide a language? A non-deterministic Turing machine M decides a language L. What does that mean? That means that for any input W, okay, what the Turing machine, the way it behaves, when it gets to a transition where there's a choice, a transition that's not deterministic, when there's a transition that's a non-deterministic transition, then basically it clones itself. The Turing machine at that point, if let's say there are 5 choices, it will clone itself into 5 different Turing machines, and in each one of those will take a different one of those choices. So the computation always looks like some kind of branching tree. Well, when there's no choice at a particular step, it takes just one branch, but when there's multiple choices, say here there's 3 choices, it branches 3 different ways. And then what does accept mean? M accepts its input W if some computation path accepts. So if one of these if one of these computations ends up with an accept, then M accepts. It doesn't matter what all the other paths are doing. If some computation path accepts and M rejects otherwise, but spelling that out even more, it means that M rejects if all paths reject. Okay? And this being a decider, because M is a decider, it means that the computation will eventually halt, which means that if W is in fact in L, then one of these paths will end up accepting. And if W is not in L, then all of these paths will end up rejecting. There's no computation path that goes on not halting in the case that W is not in the language L. Right? Okay. So that was just a little reminder of what a non-deterministic Turing machine is. And so now I can talk about how much time does a non-deterministic Turing machine take? What's its worst case running time? What's its worst case running behavior? So this is a definition. The running time of a non-deterministic Turing machine let's say M is given by, well, as a function, it's always as a function of the input size, as a function of the length of the input, N is given by the function Fm of n, which is defined as the maximum number of steps that M uses on any input of length n. Okay? So I'm going to emphasize here this is worst case. The worst case running time of a non-deterministic Turing machine M, well, it's always given as a function of the input size, the length of the input size, little n, is given by some function which we write that way. And what is it really? It's the maximum number of steps that that Turing machine M uses on any. Well, let me make this more explicit, because on any of the computations, on any of the computation paths on any input of size n. Okay, so if we look at a particular, let's say we have a particular Turing machine M, and we have some particular input. Now it's some particular input. Input W of length n. then to see what the worst case running time of this particular Turing machine M is on input W, we would look at all, this is conceptually have to consider all the possible computation paths, which means all the possible ways that the Turing machine clones itself as it's running. And we look at the termination point of all of those paths, all the different paths. Remember, this is a decider. So where does the we look at how deep does any one of the paths go? How many steps does any one of the paths in that computation go? And that is what we take as the worst case behavior, or the running time of M on input W. And then to get f of M of n, we think of all the input to M of length n. And for each one of those inputs, we think of what's the deepest, longest path that M has in its computation tree, and what's the deepest, longest path over all of the input of length n. Okay? This is kind of confusing. And I don't think the book puts in this extra clause here, this extra phrase, which is important, very vitally important in terms of the definition. So when we're talking about the worst case behavior of a non-deterministic Turing machine on input of size n, we're thinking all the possible inputs of size n, and then on each one of those inputs of size n, what's the deepest path over all the computations in the computation tree for that particular input, and then we're taking the deepest over all the possible inputs of the deepest of all the possible paths. Okay? So again, we're saying, you can turn it around if you want, and you say, well, if the worst case you can turn it around and say, here's a corollary, a consequence, just of the definitions. If non-deterministic Turing machine M has worst case running time big O, let's say, of n squared, that means as a function of its input size n, as n grows, the longest path of any computation in this Turing machine M, the longest path of any computation of Turing machine M will be bounded by a function that's big O of n squared. Okay? That you, even though, of course, there are many, many paths in the non-deterministic computation, the longest of them is bounded by n squared. That's what this definition of worst case running time in terms of a Turing machine means. Okay, I've got 2 minutes left. I just want to put down two definitions, because you're not going to be back until a week from now, but put down two definitions that are the key things of what we're going to talk about next week, which we only have 2 lectures left, believe it, in the course. And these are really critical for the major next or major last point of this course. So I've mentioned before that this course has 3 or 4 major points, and we've seen all but one. So P is equal to the set of all languages which can be decided by a Turing machine whose worst case running time is order n to the k for some k. That is polynomial. P stands for polynomial. So every language that can be decided by some Turing machine whose worst case running time is bounded by some polynomial, that's in P. And NP is equal to the set of all languages can be decided by a non-deterministic Turing machine whose worst case running time is bounded by n to the k, some k. Okay. The k can be different for each particular language. Okay. So this is a set of languages. This is a set of languages. Okay. Set of languages which can be decided by a deterministic Turing machine whose worst case running time is bounded by a polynomial. NP is the set of all languages that can be decided by a non-deterministic Turing machine whose worst case running time, that is its longest possible path, is bounded by a polynomial function of the input size. Okay? So NP, by the way, does not stand for not polynomial. Okay? This stands for polynomial. You might think NP stands for not polynomial. No, it stands for non-deterministic polynomial. Polynomial, non-deterministic polynomial. Which of these classes is bigger? We'll talk about that next week. That's the key thing we'll talk about next week.